Hi students, welcome to Year 10 Science and the physics topic of motion and energy. In this one we're going to extend our discussion of collisions and apply those discussions in the area of car safety. So one of the last examples that we looked at was our collisions during sporting activities. One of the important things that happens when we look at collisions is we have to look at systems. Now we looked at the system where the golf club actually comes into contact with the ball. And we described that in terms of Newton's third law, equal and opposite forces, which then apply a particular force on a particular mass that causes the acceleration. And that is an example of Newton's second law. The other thing we can do, of course, is we can look at the conservation of momentum. We know that during a collision, conservation of momentum occurs. That is, momentum is conserved. Now what that means is if initially the club is moving but the ball has a velocity of 0, therefore its momentum will also be 0. So the momentum of the moving golf club needs to be transferred into the entire system. That is, some of its momentum will actually be transferred into the ball as it takes off. It will have a momentum of mv, m of the ball, v of the ball if you like. The club will have decelerated because of the equal and opposite force that was placed on it by the ball, and so it will be doing some sort of an mv which will be slightly less than what it was before. Its mass, of course, won't have changed, but its velocity will be slightly less than what it was originally. That extra momentum has been transferred into moving the ball off the tee. Now, this whole concept of conservation of momentum is particularly important during car collisions. Moving cars obviously will possess kinetic energy. That is a function of their mass and their velocity, because kinetic energy is a half mv squared. But what happens if the car strikes a wall? When the car strikes a wall, the kinetic energy is converted into lots of different forms of energy: heat, sound, light, and even elastic potential energy. It's very difficult to understand where all that momentum is going, but there's a lot of transfers that occur as the car is crumpled. And in fact, most modern cars are designed in a particular way to absorb these types of collisions in such a way as to protect the occupants of the car as long as possible. One of the things that can happen is the car can transform elastic potential energy into kinetic energy if it bounces off the wall. There's an opportunity for us to actually have some sort of bounce back effect. The occupants obviously are going to experience some sort of a force as their speed decreases, in some cases quite rapidly, to 0. So if a car is moving forward at, for example, 60 kilometers an hour, and it strikes a stationary object which actually pulls it to a stop, then that's a very massive deceleration from 60 to 0 in a very short period of time. That's what can cause lots of problems. If we can increase the time over which that deceleration occurs, then we can reduce the size of the force and its impact on the individuals. This is one of the reasons why there are so many safety devices in cars that are designed to do exactly that. One of the most significant changes that occurred, certainly in the road traffic reports, was when seat belts were introduced as mandatory in cars. This significantly reduced the numbers of fatalities on the road, as the seat belts made a big difference in being able to increase the time over which that deceleration occurred and protected a lot of people, not that they would not suffer some sort of harm, but certainly not sufficient harm to cause death. We now have a number of additional safety devices, including airbags, crumple zones, in order to try and absorb again the impacts of collisions and increase the time over which that deceleration occurs in order to transfer less and less of that to the actual occupants of the car. The airbag cushions the motion forward of the driver or the passengers in all directions, whether the car hits front on, is hit from behind, or is hit from the sides. There's airbags everywhere to try and cushion the occupants and slow down the time that it takes for them to come into contact with any other surface. So safety devices in cars are about a couple of things. Firstly, increasing the stopping distance, increasing the amount of space that you have in order to slow down that rapid deceleration. Increase the time for the deceleration. So if we've got a device like an airbag, then rather than your head going straight into a windscreen or into a dashboard or into a steering wheel, the airbags come out and cushion your head. Now you may still reach each of those, but you'll reach it a little bit slower than you would have before. This does a great deal to reducing the net force, and the net force is what causes all of these problems. And part of it is the transformation of kinetic energy into other forms of energy. Sound, light, heat, all of those sorts of things pull some of the kinetic energy out of the system. The total energy remains the same, but the kinetic energy comes out of the system. We're going to have a look at another video in class that it shows you exactly the effects of braking distance and stopping distance, and also reaction times. The higher the speed, the larger a distance that you travel before you even react to a situation and apply the brakes, and then there's another distance that you travel as the brakes are applied before the car comes to a stop. This can be quite a long distance at high speeds, and all of these sorts of factors need to be taken in when we're looking at safety devices in cars. And we will have a look at these in a little bit more detail in the class. So thanks for watching.